This chapter covers the following topics: PLC programming concepts, basic ladder diagram programming, and basic function block diagram programming. Completion of this chapter will help you learn important PLC terms and develop an understanding of PLC programming concepts. Siemens Totally Integrated Automation Portal, TIA Portal, software is used in all phases of automation system design, operation, and maintenance. TIA Portal combines the software editors needed for these various tasks into one engineering tool. The user can choose between the portal view, which guides the user through each engineering step, or the project view, which offers fast access to all relevant tools. The portal view is a good place to start for a new user or anyone who wants to proceed with the development of a project in a logical sequence. In Portal View, the available tasks are clearly identified, such as create new project, configure a device, or write PLC program. Selecting configure a device allows the user to quickly and easily set up a new device. Device types are easily located in a searchable hardware catalog. Configuration and networking for the entire project are performed in the device and network views, which display graphical representations of devices and allow network connections to be created using a simple drag-and-drop approach. Configuration is further simplified by using TIA Portal to detect connected devices. For example, the accompanying graphic shows a TIA Portal project view after an S7-1200 PLC has been detected. In this graphic, a picture of the S7-1200 PLC is superimposed on the TIA Portal screen to show how realistic the device image is. Preparing a PLC for use in an automation system requires configuration of devices and networks and programming of the PLC and related devices. For Siemens PLCs, the following engineering software is used to perform these functions. S7-200 PLCs require Step 7 Micro Win, which is not available in the TIA Portal. S7-300 and S7-400 PLCs require Step 7 Professional TIA Portal, or a version of Step 7 Professional which is not in TIA Portal. S7-1200 PLCs require Step 7 Basic TIA Portal or Step 7 Professional TIA Portal. S7-1500 PLCs require Step 7 Professional TIA Portal. Step 7 engineering software runs on a personal computer, PC, that has a Microsoft Windows operating system. Siemens sells a variety of industrial PCs that can be used as programming devices. For added convenience, the Semantic Field PG comes with pre-installed Semantic TIA Portal engineering software and is optimized for mobile configuration, commissioning, servicing, and maintenance of an automation system. Step 7 Basic TIA Portal is used for the configuration and programming of S7-1200 PLCs and related devices. This can also be done using Step 7 Professional TIA Portal. However, Step 7 Basic is a more economical approach when other PLC models are not being used. Step 7 Basic supports the following IEC 61131 programming languages. Ladder diagram, LAD, shown in the accompanying graphic, is a graphical programming language originally derived from the diagrams used in electromechanical control circuits, but which has been expanded to include much more advanced capabilities. Function block diagram, FBD, is a graphical programming language similar in capabilities to ladder diagram programming. Structured text is a high-level programming language that is also known as Structured Control Language, SCL. SCL is particularly suitable for the programming of complex algorithms and arithmetic functions. Step 7 Basic allows program elements to be dragged and dropped into the program and the logical arrangement of these elements to be modified in the same way. As shown in the accompanying graphic, a user program for an S7-1200 PLC can include a full range of instructions such as Boolean logic, counting, timing, comparisons, math, and much more. In addition, commonly used instructions can be easily saved as favorites for convenience. Step 7 Professional TIA Portal is used for the configuration and programming of S7300, S7400, S71200, and S71500 PLCs and related devices. Because S7300 and S7400 PLCs were developed prior to the introduction of TIA Portal software, a version of Step 7 Professional separate from TIA Portal is also available for use with these PLCs. In addition to the LAD, FBD, and SCL programming languages included in Step 7 Basic, Step 7 Professional also includes the following IEC 61131 programming languages. Statement List (STL) is a low-level text-based programming language. Statement List is also known as Instruction List (IL). Sequential Function Chart (SFC) is a graphical programming language included in Step 7 Professional as S7 Graph. In S7 Graph, steps are shown in a sequence, making it easy to see the order in which events will occur. Step 7 Professional also includes S7 PLC Sim software, which simulates a controller for functional testing of user blocks and programs on the programming device. A PLC executes its program in a cyclic manner referred to as a scan. A PLC program can be organized as a linear program or a modular program. As shown on the left in the accompanying graphic, a linear program has all the instructions in one block and executes these instructions in sequence in each PLC scan. A linear program works well when the program is simple and does not need to vary from one PLC scan to another. As shown on the right in the accompanying graphic, a modular program is composed of multiple program blocks. Some program blocks are executed in each PLC scan, and other program blocks are executed under special circumstances, such as during startup, at specific times, when a special process event occurs, or when an error or interrupt occurs. An interrupt is a special signal or condition that causes a PLC to immediately perform a specific task. In programming terminology, when a program block initiates another program block, the initiating program block is said to call the other block. This causes the calling program block to temporarily halt its execution until the called program block completes its execution. Then the calling block resumes its execution. As shown in the accompanying figure, program blocks can also be nested. This means that one program block can call another program block, which can call another program block. This provides additional flexibility in programming. As compared to a linear program, a modular program with program blocks that perform functional tasks is easier to understand, develop, and debug. In addition, a modular program often performs better because it can vary the tasks from one PLC scan to another based on the needs of the application. An S7 PLC program can include data blocks, DBs, and three types of program blocks: organization blocks, OBs, function blocks, FBs, and functions, FCs. Program blocks, also called code blocks, are blocks that include instructions. The term function block does not mean the same thing as function block diagram, FBD. FBD is a programming language, and any of the three types of program blocks can be programmed in any of the allowed programming languages. OBs define the structure of the program. Every program must have at least one OB. If it has only one OB, that block is identified as OB1. In a linear program, all the code is in OB1. A modular program can be composed of multiple OBs, each with a unique number. OB1 is the main program block, and it controls the execution of the user program. OB1 is also called a program cycle OB because it is executed each scan cycle while the CPU is in run mode. A PLC program can have additional program cycle OBs as well as other types of OBs that are executed conditionally, such as at startup, at set time intervals, or when an interrupt occurs. FCs and FBs contain the program code that performs specific tasks. An FB uses an associated DB. An instance DB stores data for one FB. A global DB contains data that is available to any code block. An FC cannot have an instance DB, and the output data values from the FC must be written to memory addresses or to a global DB. FCs and FBs are often referred to as subroutines. A subroutine is a portion of a program that is executed when certain conditions are met. A common modular program application involves one PLC controlling multiple machines or devices with the same functionality. For example, a factory may have multiple motors that must be controlled in the same way by the same PLC. As shown in the accompanying graphic, this can easily be done using one FB that is called multiple times per PLC scan using a different instance DB for each motor. S7 CPUs have the following memory areas: load memory, work memory, retentive memory, local memory, and global memory. The amount of each memory type available varies with the CPU model. Load memory stores all code blocks, data blocks, technology objects, and hardware configuration. Load memory is retentive memory, which means that its contents are retained in the event of a power loss. Load memory for an S7-1500 CPU is stored on a somatic memory card. Load memory for an S7-1200 CPU can be stored either in the CPU or on a somatic memory card. A somatic memory card can also be used to transfer the user program and data to another CPU. The CPU copies some elements of the user program from load memory into work memory during program execution. Work memory is volatile memory, which means that the contents of work memory are lost when power is lost, but the CPU restores work memory contents when power is reapplied. Work memory in an S7-1500 CPU is divided into two areas: code work memory and data work memory. Code work memory contains parts of the program code. Data work memory contains parts of the data blocks and technology objects. Retentive memory is non-volatile memory for saving a limited quantity of data. For example, the tags and operand areas that have been defined as retentive are saved in retentive memory. Local memory L is temporary memory used during the processing of a program block. Global memory is memory that is accessible to any program block in the user program. Global memory includes bit memory M and image tables for inputs I and outputs Q. Most instructions in a PLC program interact with one or more bits, bytes, or words in the CPU memory. The amount of memory used depends on the type of instruction. The specific memory locations used are identified by operands. For example, the instructions shown in the accompanying graphic each use a 1-bit memory location. The operand for the normally open contact instruction indicates that this instruction is controlled by the I2.4 status bit, and the operand for the output coil instruction indicates that this instruction controls the Q3.2 status bit. This type of operand is called an absolute operand and is preceded by the percent symbol when displayed in Step 7 TIA portal. Step 7 also allows use of alphanumeric tags as operands. Tags are useful because they aid understanding of the program. A tag preceded by # is assigned to one program block. A tag enclosed in quotation marks is available to any program block. For example, a normally open contact instruction might have a tag such as Start Motor 2 to indicate that it is being controlled by the Start push button for Motor 2. Or an output coil instruction might have a tag such as Motor 2 to indicate that it is controlling Motor 2. As shown in the accompanying figure, one way a tag can be created is by assigning it to an instruction in the user program and then dragging the tag to the associated input or output in the device view. As tags are created in the user program, they are also added to the PLC tag table. Another way to create a tag is by entering it into the PLC tag table directly and then dragging the tag to an input or output in the device view. With either approach, the PLC tag table is a useful tool for keeping track of tags. To determine how an instruction in a PLC program interprets bits in the locations designated by the instruction's operands, you must know the data type the instruction assigns to these bits. There are many data types, and they are often represented by shorthand names such as dword or sint. For example, the accompanying graphic shows a multiply instruction with assigned integer int data type. As shown in the lower part of this graphic, the instruction's data type can be easily changed. When making this selection, make sure that the data type is compatible with the instruction's operands. PLC data types of various lengths are specified for binary numbers, integers, floating point numbers, date and time, characters, parameters, system data, and other types of data. Because the number of data types has increased over time, not all data types are available for all Siemens PLCs. The accompanying table shows the binary number, integer, and real number data types available for some modular Siemens PLCs. Additional information on these and other data types is available in the documentation for each PLC model. Ladder diagram programming, LAD, also called ladder logic, is a graphical programming language derived from the diagrams used for electromechanical control circuits and expanded to include more advanced capabilities. The accompanying graphic shows two completed LAD networks and one network yet to be programmed. The networks are numbered beginning with the top network, network 1. Because networks resemble rungs of logic, a network is sometimes referred to as a rung. As the CPU executes the user program, it scans each network from left to right, beginning with the instructions closest to the power rail, which is the vertical line shown on the left in each network. One of the ways that PLCs use binary bits is to represent the on or off condition of inputs and outputs. Within an S7 PLC CPU, there is a portion of memory referred to as the process image. The process image has a bit assigned to every possible input and output, even if those inputs and outputs are not connected to devices. For example, input 2.4, I2.4, is associated with input bit 4 of input byte 2 in the process image. Input I and output Q bits in the process image, along with a type of memory called bit memory, M, are collectively called global memory because these memory areas are available to all code blocks. Instructions like the ones shown in the accompanying graphic that perform logical operations using single-bit memory locations are referred to as bit logic instructions. Because the LAD programming language includes many instructions, Step 7 groups instructions into categories. As the accompanying graphic shows, there are a number of basic and extended instruction categories. This lesson provides examples of some of the instructions in the bit logic category. Even though a network in a LAD program is an arrangement of computer instructions, each network is said to control power flow from the power rail. In programming terminology, this examination of logical conditions is called solving the logic, and the solution of a configuration of instructions is called the result of logic operation, RLO. For example, when the normally open contact instruction shown in the accompanying graphic permits power flow to the output coil instruction, the RLO to the output coil instruction is a logic 1, and the output coil instruction is executed. When the normally open contact instruction does not permit power flow, The RLO to the output coil instruction is a logic 0, and the output coil instruction is not executed. Next, consider the upper network in the accompanying graphic. The normally open start motor 2 contact instruction is in parallel with the normally open motor 2 contact instruction, and power must flow through one or both of these contact instructions to get to the stop motor 2 normally open output contact instruction. Then the stop motor 2 normally open contact instruction must permit power flow in order for the motor 2 output coil instruction to turn on. Although the lower network in the accompanying graphic has different connections, the logical solution to both networks is the same. Admittedly, as the lower network is solved by the CPU, the stop motor 2 contact instruction is examined first, but that does not change the conditions under which power flows to the output coil instruction. The accompanying graphic shows 4 LAD instructions. Do not confuse these instructions with electrical devices. These are instructions that follow simple rules. The normally open contact instruction is closed and will pass power flow when the status bit specified by the operand is 1. The normally closed contact instruction is closed and will pass power flow when the status bit specified by the operand is 0. The output coil instruction sets the status bit specified by the operand to 1 when the instruction receives power flow. The inverted output coil instruction, which is not available for S7200, S7300, and S7400 PLCs, sets the status bit specified by the operand to 1 when there is no power flow to the instruction. To understand how these rules work, consider the network shown in the accompanying graphic and the truth table for this network. The truth table shows all the possible logical combinations associated with a network and the resulting output condition for each combination. Because this network includes 2 series contacts, both contacts must be closed to pass power to the output coil instruction. For this to occur, I2.4 must be 1 and I3.5 must be 0. When this condition exists, Q3.2 is 1. Otherwise, Q3.2 is 0. Next, consider the truth table for the lower network in the accompanying graphic. The final instruction in this network is an inverted output coil instruction. The inverted output coil instruction gets its name from the fact that it turns on when the RLO to the instruction is 0, which is an inverted result from that of an output coil instruction. In this example, when I2.4 is 1 and I3.5 is 0, there is power flow to the inverted output coil instruction, and output Q4.1 is 0. LAD programs incorporate configurations of instructions that represent logical conditions derived from the Boolean logic used to design computer circuits. Some of the more common Boolean logic functions are the AND, OR, and exclusive OR functions. For example, the network in the accompanying graphic is an AND function. For this network, as the associated truth table shows, the only condition that causes the output coil to turn on and the Q3.2 status bit to be set to 1 is when I2.4 and I3.5 status bits are both 1. In other words, when the status bits for both normally open contact instructions are 1s, both contacts will be closed and there will be power flow to the output coil instruction. When normally open contact instructions are placed in parallel leading to an output coil instruction, an OR function is formed. For this network, as the associated truth table shows, if the status bits for either or both of the normally open contact instructions are 1, the Q3.2 status bit is set to 1. The exclusive OR function is formed using normally open and normally closed contact instructions leading to an output coil instruction. As the truth table for this function shows, Q3.2 is 1 if either I2.4 or I3.5 is 1, but not if both are 1s. The inverted output coil instruction is one example of inversion, which means changing a 1 to a 0 or a 0 to a 1, and is sometimes called negation. To understand this better, consider the networks shown in the accompanying graphic. The AND and OR functions previously described are shown along with similar logic that uses an inverted output coil instruction. This results in logical operations that are sometimes referred to as NAND and NOR functions. Notice that the truth tables for these functions show the resulting states for Q3.2 to be inverted in comparison to the truth tables for the AND and OR functions. The not contact instruction shown in the accompanying graphic is another example of a logic inverter. If there is no power flow to the not contact instruction, there is power flow after the not contact instruction and vice versa. Note that the truth table for the network with the not contact instruction shows the states of output Q3.2 as inverted from the states shown for the network without the not contact instruction. Because the inversion occurs each time the network is scanned, the not contact instruction does not have an operand. Although S7200, S7300, and S7400 PLCs do not have an inverted output coil instruction, adding a not contact instruction prior to an output coil instruction has the same effect. There are a variety of LAD instructions for setting and resetting bits. For example, the accompanying graphic shows networks with set and reset coil instructions. When there is power flow to the set coil instruction, the bit specified by the instruction's operand is set to 1. When there is power flow to the reset coil instruction, the bit specified by the instruction's operand is reset to 0. In this example, when I2.4 is set to 1, the normally open contact closes, there is power flow to the set coil instruction, and Q3.2 is set to 1. Output Q3.2 remains a 1 even if I2.4 later goes to 0. When I4.3 is 1, there is power flow to the reset coil instruction, and Q3.2 resets to 0. The accompanying graphic shows a set-reset flip-flop, another instruction that sets and resets bits. When there is power flow to the set S input, the output Q and the memory bit specified by the operand at the top of the instruction are both set to 1. They remain a 1 even if there is no power flow at the set input, until there is power flow at the reset R input. For the set-reset flip-flop, the reset input is dominant. In other words, with power flow at both the set and reset inputs, the output and memory operand for the set-reset flip-flop are both 0. Next, consider the lower network in the accompanying graphic, which includes a reset set flip-flop instruction. This instruction functions the same as a set-reset flip-flop instruction, except that the set input is dominant. In other words, with power flow at both the set and reset inputs, the output and memory operand for the set-reset flip-flop are both 1. In the example shown, note that a bit memory M address is used as an operand. Using a bit memory address rather than an input I or output Q operand avoids the problem of picking an operand that could otherwise be used by the PLC's I/O modules. Instructions shown in this lesson are only a few of the many types of instructions that can be included in a Siemens PLC LAD program. A LAD program can include a variety of basic and extended instructions. The basic instructions are grouped in the following categories: bit logic instructions, timers, counters, compare instructions, math instructions, move instructions, convert instructions, program control instructions, word logic instructions, and shift and rotate instructions. The extended instructions are grouped in the following categories: clock and calendar, string and character, program control, communications, interrupts, PID, motion control, and pulse. In combination, the basic and extended instructions provide an extensive set of instructions that allow Siemens PLCs to perform the full range of automation tasks. Function block diagram programming, FBD, is a graphical programming language similar to LAD programming. And like a LAD program, an FBD program or program block is composed of numbered networks. As shown in the accompanying graphic, an FBD program is made up of instructions that use the same types of operands and tags as a LAD network. As with a LAD program, in Step 7 TIA Portal, an absolute operand is preceded by %, a global PLC tag is enclosed in quotation marks, and a local tag, which is a tag defined in a program block for use only by that program block, is preceded by the £. Step 7 TIA Portal also provides the option to display absolute operands and tags at the same time as shown in the accompanying graphic. Because the FBD programming language includes many instructions, Step 7 groups instructions into a number of basic and extended instruction categories. These instructions provide FBD with similar capabilities to those of LAD programs, and in some cases the instructions look the same. However, there are some important differences. Some of those differences are shown in this lesson, which provides examples of instructions in the bit logic category. As the PLC scans the user program from top to bottom in a program block, each network is scanned from left to right. Just as with the LAD program, the solution for a configuration of instructions is called the result of logic operation, RLO. Using the simple network shown in the accompanying graphic as an example, the two instructions on the left are solved first. The logical solutions to these instructions are provided as inputs to the next instruction. The logical solution to this instruction is provided to the final instruction, which in this example assigns the result to an output status bit in the process image. As shown in the accompanying graphic, the assign instruction is the FBD equivalent to the LAD output coil instruction, both of which store the logical result of the network in the memory location specified by the operand. When the RLO to the assign instruction is 1, the instruction sets the operand to 1. When the RLO to the assign instruction is 0, the instruction resets the operand to 0. Some FBD bit logic instructions are derived from Boolean logic. One of the most common of these instructions is the AND instruction. The accompanying graphic shows an AND instruction with 2 inputs, but an AND instruction can have 3 or more inputs. The operand associated with each instruction input identifies the memory location where a 1 or 0 is stored. In this example, only I operands are used. However, Q and M operands can also be used. As the associated truth table shows, the result of the AND operation is 1 when both of the inputs to the instruction are 1s. When there are more than 2 inputs to the AND instruction, all inputs must be 1s for the result to be 1. The AND instruction can be combined with other instructions to form a network. In the accompanying graphic, the AND instruction is combined with an assign instruction that controls the output Q5.2 status bit in the process image table. In this example, output Q5.2 is 1 when I3.1 and I4.2 are both 1s. The OR instruction is another FBD bit logic instruction. The accompanying graphic shows an OR instruction with 2 inputs, but an OR instruction can have 3 or more inputs. In this example, the instruction inputs are I operands. However, Q and M operands could have been used. As the truth table shows, the result of the OR instruction is 1 when 1 or more of the inputs to the instruction are 1s. The OR instruction can be combined with other instructions to form a network. In the accompanying graphic, the OR instruction is combined with an assign instruction that controls the output Q5.2 status bit in the process image table. In this example, output Q5.2 is 1 when 1 or both of the inputs are 1s. The accompanying graphic shows an FBD exclusive OR instruction with 2 inputs, but an exclusive OR instruction can have 3 or more inputs. In this example, the instruction inputs are I operands. However, Q and M operands can also be used. As the truth table shows, the result of the exclusive OR instruction is 1 when one of the inputs to the instruction is a 1, but not when both are 1s. This rule must be expanded to take into consideration exclusive OR instructions with more than 2 inputs. The broader rule is that when an odd number of instruction inputs are 1s, the result is a 1. But when an even number of inputs are 1s, or when all inputs are 0, the result is 0. FPD instructions are often combined to form networks that perform more complex functions. For example, the accompanying graphic shows a network of 5-bit logic instructions. By analyzing the truth table shown, you can determine the status of output Q6.2 for any combination of operand statuses. Inversion, also called negation, means to change a 1 to a 0 or vice versa. When applied to FPD programming, an invert instruction is represented by a small circle adjacent to another FPD instruction. The accompanying graphic shows an example of an invert instruction on one input of an AND instruction, but the invert instruction can be used with other FPD instructions as well. As the associated truth table shows, the result of this logic combination is 1 only when I3.1 is 0 and I4.2 is 1. Without the invert instruction, the result is 1 only when both inputs are 1s. Another type of inversion available for S7-1200 and S7-1500 PLCs is the Negate assign instruction. The Negate assign instruction inverts the RLO of a network. Therefore, if the RLO of the network is a 1 without the Negate assign instruction, the RLO is a 0 with the instruction and vice versa. For example, the accompanying graphic shows a network with an OR instruction connected to a Negate assign instruction. As the associated truth table shows, the result of this network is a 1 only when both of the inputs to the instruction are 0s. With an assign instruction instead of a negate assign instruction, the result is a 0 only when both inputs to the instruction are 0s. There are a variety of FPD instructions that set and/or reset bits. For example, the accompanying graphic shows a set instruction. When the RLO to the left of the set instruction is 1, the instruction sets the specified bit to 1. In this example, when I3.1 and Q2.1 are both 1s, the set instruction sets output Q4.2 to 1. Output Q4.2 remains a 1 even after the result of the AND instruction returns to 0. The accompanying graphic also shows a reset instruction. When the RLO to the left of the reset instruction is 1, the instruction resets the specified bit to 0. In this example, when either I3.2 or Q5.1 or both are 1s, the reset instruction resets output Q4.2 to 0. Output Q4.2 remains a 0 even after the result of the OR instruction returns to 0. The accompanying graphic shows 2 other instructions as set and reset bits. The top network includes a set-reset flip-flop, and the bottom network includes a reset-set flip-flop. Both networks perform a similar function. When there is a 1 at the set S input, the output Q and the memory bit specified by the operand at the top of the instruction are both set to 1. They remain a 1 even after the set input goes to 0 until there's a 1 at the reset R input. There is one important difference between these instructions. For the set-reset flip-flop, the reset input is dominant. For the reset-set flip-flop, the set input is dominant. If there's a 1 at both the set and reset inputs, the dominant input controls the result. The instructions shown in this lesson are only a few of the many types of instructions that can be included in a Siemens PLC FPD program. An FPD program in a Siemens PLC can include a variety of basic and extended instructions. As you have seen, some of the FPD instructions are different from corresponding LAD instructions but the instruction categories and overall capabilities of FBD and LAD are very similar. This chapter has provided you with information on PLC programming concepts, basic ladder diagram programming, and basic function block diagram programming. The concepts and terminology discussed in this chapter will be useful to you in furthering your knowledge of Siemens PLCs. Proceed to the final exam to complete this course.